All right, so if I have a dipole here, and I'm at some point out here, so this is some point P. I probably should use a different letter since P is now an electric dipole moment. So at some point out here, we'll call M. I'm not using M for anything right now. I want to know what is the electric field at this point M. Now I know that if this distance from here to here is large enough, we'll call that R. If this is large enough, then my electric field should be close to zero because I have two charges that are opposite here, each exerting an electric field onto it. And they should somewhat cancel out if I'm far enough away. If I'm in between them, there definitely is an electric field that's traveling in the negative P direction. If you recall, P, the electric dipole moment, is a vector going that way. But the electric field would be going in this direction here, but far enough away it should be close to zero. So whatever we derive right now, that is a test that we can take. So let's actually go through the derivation. So I know that the electric field at this point is going away from positive, and it's going towards negative. And so let's come up with an angle here. So this, if this distance here is S, then the distance for that would be half of S. And let's draw that. So I have S over 2. Basically, I have a right triangle here. This is R, and so therefore this is the square root of R squared plus 1/2 S squared. So I can find this angle right here, theta, and set up a coordinate system here. So I have I hat and J hat. So the electric field so the total electric field should be the electric field at point M from the positive charge plus the electric field at point M from the negative charge. I have two electric fields, I add them together, but I add them like vectors. I know, given this angle right here is theta, this angle here is theta, and that angle there would be theta because of symmetry and geometry. And so I've got from the positive charge here, well, I know whatever the charge is, the electric field in the positive I direction is going to be equal but opposite to the electric field in the negative I direction, just because, again, of symmetry. I mean, we can go through to do the calculation, but that's what it's going to be. And so let's do some vector addition here. So my EM positive, so the electric field at point M from the positive charge, is going to be the magnitude of the electric field from the positive charge times the cosine of theta I hat minus sine theta J hat. So typical, just breaking up a vector based upon the angle here, hypotenuse times the cosine, hypotenuse versus the sine, and it's negative because negative J hat because I said J hat was positive going that way. EM negative is going to be the magnitude of the electric field from the negative charge times negative cosine theta I hat minus sine theta J hat. Now the electric field magnitudes, I know that the electric field is going to be equal to the electrostatic constant times the charge divided by the distance between them squared. Well, that's the distance from point M to that charge or to that charge. It's the same distance. So if I square that, I get little r squared plus 1/4 S squared. And that's a 1/4 there. Let me write that a little bit better. Plus 1/4 S squared. And it's the same for either of them because they have the same magnitude. That's positive Q and that's negative Q. This is a dipole here. That's a positive Q and a negative Q. So this E is the same. And so when I add them together, I distribute, add them together, the I components will cancel out. And so what I'm left with is the electric field at point M is negative 2 times the magnitude of the electric field times the sine of theta J hat. Well, That'll be negative 2 times k sub e q over r squared plus 1/4 s squared times the sine of theta. Coming back to this chart over here, sine of theta will be opposite over the hypotenuse. So this becomes 1/2 s divided by that distance there, which is the square root of r squared plus 1/4 s squared. So opposite over hypotenuse, j hat. And now we have some canceling out that goes on. That 2 and that 1/2 cancel out. So now I'm left with negative k e q s over r squared plus 1/4 s squared to the 3/2, j hat. Now recognize that my electric dipole moment is in the positive direction, the positive j hat direction. And the magnitude of the electric dipole moment is equal to the distance between them, which is s, times the charge. That's the magnitude of it. Hey, that is exactly what we have right here. And since it's in the j hat direction, that is my electric dipole moment. So I'm left with negative the electrostatic constant times p vector. And again, this is the electric dipole moment. It is not momentum. Over r squared plus 1/4 s squared to the 3/2. And now it comes down to exactly how do you want to work it out. Please note that if s is 0, if r is 0, then we end up with the electric field smack dab in the middle. If r goes to infinity, then this denominator becomes incredibly huge, which means that the electric field goes down to 0, which is a quick check. So we've done something at least reasonable. If we're not an infinite distance away, let's formally write that out. That means the electric field goes to 0. If r is just big, but not infinitely large, but if r is much greater than the distance between them, well, let's work through that. So what I want to do is I want to factor r out. So I get negative k e p vector, k sub e p vector. And I factor that out, so I get r cubed, because I factor out the r squared, and that's r squared is raised to the 3/2. 1 plus s squared over 4r squared to the 3/2. So if r is much bigger than s, then this term right here goes to 0. And what we're left with here is negative k sub e p over r cubed. And so that is the electric field if we are far away, not infinite distance away, but we're far away from the dipole.